Okay, hopefully everybody can see my screen. Once again, thank you for joining the end of project review. My name is Urmi Ray. I'm going to kick off the meeting today. I'm the iNEMI program lead, program manager. This project has been ongoing for about close to 2 years, a little under 2 years, under the tutelage of co-chairs Sai Fumakasani, Richard Stevenson, and Dr. Changshen Chen. We have a very active technical working group that is stated here, and you can see the people in there that have been really leading and guiding the project. We are also recording the webinar, and the webinar recording will be available for others who are not able to join the project today. So quickly, the agenda for today is I'll go through and provide a brief introduction with the project goals and the timeline that was stated in the original SOW statement of work, followed by tasks 1 and 2 that are going to be actually presented by Marzena, but the material has been prepared by Marzena and Sai. The task 3 would be reported by Mike Hill of Intel, and task 4 would be tag teamed by Lucas and Nate from NIST, who will also take us through the summary and next steps, which is the follow-on project that we are kicking off. Okay. As I stated before, if you have, please mute your phones or audio, and then if you have any questions, you can put them on the chat and we will address them at the end. So first of all, we wanted to really thank the project team. As you can see, we have a really large project team. We had 26 members as we started the project. Majority of them have been very active throughout the project, including guiding, writing reports, as well as providing materials for evaluation. So it's been a pleasure really working with the team. And so first of all, I really need to thank the project team for this amazing work and teamwork. Just a quick perspective of why we started this project. This is a chart courtesy of Intel, but it basically states the problem. What we know is 5G communications. We just generally state 5G, but it's millimeter wave. We know it requires very different communication challenges and requires very reliable methods of characterizing the materials. Basically, if you don't do that properly, you end up being iterating through multiple design and build cycles, which is not only extremely expensive. For example, you can see the Intel, evaluation of those costs. So not only is it very important, cost prohibitive, but it's also time prohibitive because, as we all say, time is money, right? So we went together, the group came together and said there's a very strong need to come together and work cooperatively, pre-competitively on coming up with reliable characterization techniques for low loss type of materials that are used in millimeter wave technology. And so iNEMI brought this group of people together to define the problem, and you can see the global team here. It's across the globe, many different different countries participating in this effort because truly it is a global problem for millimeter wave communication, right? And so what we said in the beginning is, what's really the problem statement? As I mentioned before, these materials pose the challenges in that there is no consistent methodology for measuring key parameters such as the transmission loss and the permittivity of materials at higher frequencies. And throughout the industry, over the, people have been using these materials, right? But there are many different characterization methods. Different approaches are used, using different fixtures, test methods, etc., sample preparation. And there was really a lack of consistency for data measurement as well as data analysis and extraction. So what we did was, in the beginning of the project, this industry group said, okay, we needed to come up with the following tasks. Firstly, we wanted to benchmark the current industry best practices, really coming up with a report outlining the current measurement methods, reference standards, sample preparation, etc., which basically formed the basis for recommendations for how to reliably measure materials, which is actually in task 3. In addition to benchmarking current industry methods, we also undertook a methodology to benchmark the next generation, the research efforts into the new areas, new emerging methods for measurements, because we know how fast technology moves. So current today versus current in 5 years, methods may not be the same thing. So we wanted to also benchmark that process. And then the key task in terms of measurement and looking at collaboration is the development of best practices. And that really incorporated round robin evaluations with an output that we will discuss a little bit later. Followed by what I find a very, very important part of of this whole project, which is actually evaluation, validation of the best practices using round robin of commercial candidate materials. And we were really lucky and fortunate to have industry partners submit candidate materials, and we could validate our methodology by using the commercial candidate materials. And then task 5 was the end of project webinar, which is what we're doing today. So as always, any project, we go through a project SOW as well as a timeline, and we've gone through all of these phases and tasks. We are a little bit behind, in terms of planning. It's instead of 16 or so rather 6 quarters, we are at about 7 quarters. But given the immensity of the work, I think it's time well spent is what I think you would also agree here. So that's basically my introduction for this project. What I'm going to do is hand it off to Marcena, who will take us through the tasks 1 and 2 summary. But before that, I just wanted to give you really what should I say, project health check. You can see that we've completed the 4 tasks as we have outlined before. You'll also see, our list of partners that in this project that have spanned the entire value chain of the electronics industry, and that is what we are very happy to report here. So with that, I will hand it off to Marcena, who's going to take us through the next set of the presentation. Marcena?
Yes, thank you, Urmi. Yes, I will say a few words about task 1 and task 2. And let me start, obviously, with task 1, which is benchmarking current measurement techniques. Within this task, as you probably all know and are aware, with new material coming through development process and to the use, we need to carefully consider how to approach its characterization, which test fixture to choose, which measurement methodology will be the most suited one, how to fabricate the sample to make sure that we are getting high accuracy of our characterization. And of course, on the market, there are there is a wide spectrum of available solutions, and the the decision which to choose is not so obvious. So within this task one, we wanted to benchmark the currently existing methods to answer some of those questions. And we focused actually on resonant measurement techniques, which include split pulse dielectric resonator, split cylinder resonator, balanced circular disc resonator, and Fabry-Perot open resonator. And all of those techniques actually span a very wide frequency range, and you can see how each of the techniques is situated over the frequency range. And what you can see, those which are the most broadband and go up to over 100 gigahertz are the two of them, Fabry-Perot and BCDR methods. What we did, if I may ask another slide, the following slide, what we did, we evaluated features of those four methods to see what we can achieve with them, where are the limitations for those methods, and to which application they are suited. So starting with the SPDR, we know that those test fixtures work at discrete frequency points. They are available from 1 gigahertz up to 15 gigahertz. They are easy to use, assure high measurement precision. What they bring us is the in-plane component of the permittivity. And based on results achieved with those measurement techniques, we can extrapolate the values to 5G millimeter waves range. The next one, which is split cylinder resonator, it also operates at discrete frequency points. So we have a single device at a single frequency, but this one spans over a wider frequency range, or rather up to higher frequencies. It also gives us high measurement precision. It delivers information about in-plane component of the permittivity, and also similarly as PDR can support temperature sweep measurements. From those two, we treat the SPDR, which is in the lower frequency range, as a kind of reference, or may treat as a kind of reference method. If we can switch to another slide. The two following two methods are concerned with higher frequency range, and the first one is balanced circular disc resonator, and for which we get multiple discrete frequency points from a measurement, and this spans typically from 10 gigahertz to 120 gigahertz. Again, we get a very high measurement precision. The drawback here is that we need a full two-port calibration. What differs this solution from the others is that we get an out-of-plane component of the permittivity here. But what we need also here are two exactly identical samples for a single measurement, whereas for the rest of the solutions we need only one. And the last one, which is Fabry-Perot open resonator, is similar to the BCDR in terms of the fact that we are getting permittivity at multiple discrete frequencies from a single measurement. The solution that we extensively used in the further actions was dedicated to measurements from 20 to 110 gigahertz, but commercially available solutions span up to even 330 gigahertz. The Fabry-Perot gets us with high precision measurement, but it can be sensitive to user errors. It gets us in-plane components of the permittivity, similarly like SPDR and SCR, but some of the solutions allow for distinguishing the in-plane anisotropy of the material if it appears. So having all those devices, the question arises, if we can switch to another slide, the question arises how to validate the accuracy of those devices and how to verify them. We answered this question, and the conclusion was that we need a kind of standard reference material, which are stable materials, precisely fabricated, of non-material parameters that we can use in each of the devices and then cross-validate those devices. And also validate against the nominal values of the material parameters of those materials. So what we did within the task one, we listed some candidates for the standard reference materials. You can see them on the slide. Those are the COP material, Rexolite, PTFE, fused silica, and sapphire. We evaluated on the basic parameters of those materials, like approximate thickness, which is available, whether those materials are isotropic or anisotropic. Most of them are said to be isotropic. Only the sapphire from the candidates is an isotropic material. We also made some conclusions or notes on the easiness of machining them, or whether they are easy to machine, harder to machine, how we can easily can handle them. For the COP, for example, we concluded that finger oil may somehow influence the measurement unless we are using the gloves. So those are the materials that we concluded to be candidates for standard reference materials, and actually some of them were used by us in the task 3 as reference materials for the round robin activities. If we can switch, yes. So having all those devices and already candidates for standard reference evaluate where the sample dimensions. Each of the devices comes with their own requirements on the sample dimensions, both in lateral size but also the thickness. We have evaluated that. We have put that in the table, compared, and the challenge which was approaching was to find a common sample size which will allow us to cross-validate, cross-reference between all the devices and techniques, to make, and the sample size should cover the highest possible number of devices to make the results, our study, meaningful. So that was that were the main tasks or activities performed within the task 1, which resulted in an extensive report giving all this information I briefly described. And the following task, which was actually going simultaneously, was the task number 2, in which the benchmarking emerging measurement and characterization methods was performed. This task aimed at distinguishing methods which are our future. So for the higher frequency ranges, the methods that were listed or in the report were mainly the transmission line methods, where we use, for example, waveguides. With these methods, we can go up with the frequency, and the limitation or this frequency range is limited with the size of our device, like a waveguide. The other methods that are used, or which we considered, were free space methods, like the one shown on the slide, in which we are using 2 antennas, the sample between them. We are performing a measurement of transmission coefficient and also the reflection coefficient. With this method, we can go up beyond 100 gigahertz with our characterization of materials. The third one is the microstrip ring resonator. What you can see on the slide are examples of this kind of device operating in the D band, so between 110 and up to 170 gigahertz. So those are our listed candidates for higher frequency material characterization. And the one that is even going further is the time domain method, which is called TD, so time domain spectroscopy, so TDS. This is, as mentioned, a time domain method. So, so what we can get from it is extracting material or the dielectric properties as a continuous function of frequency, in contrast to frequency domain methods, which we discussed in task 1. But what we need to also, and this method spans over a very wide frequency range, going up to even 2 terahertz. But what we need to be aware of is that the resonant methods considered in task 1 are well defined, well known. They are known to get the highest possible accuracy at the moment, and in these new methods, the new methods are a bit more advanced in terms of taking into account the uncertainty causes. Like, for example, in the TDS method, we need to strictly account on the scattering effects which may appear on the sample, which may degrade our accuracy. But that's the future, and we hope this will continuously evolve and get us to a point where the accuracy of those higher frequency methods are high. And I think I can hand over to Mike to go on the task 3.
Yes, thank you, Marzena. That was a really excellent summary. And now we transfer over to Mike Hill of Intel, who's going to give us the summary of task 3. So, Mike.
Okay, thanks. So task 3 was the round robin experiment. And as a reminder for people who have sat through some of these presentations before, we had 10 labs scattered across the world who had these 4 measurement pieces of equipment that were identified from task 1 and 2, the SCR, the SPDR, VCDR, and FPOR in their labs. And all of these labs have had a fairly large amount of experience doing these types of measurements with their own equipment sets. So we identified these as the candidates for doing the round robin experiment. Out of the task 1 and 2, we also had identified a number of material samples. And if you go on to the next slide, the material samples that sort of fell out as natural candidates for this round robin experiment were the Teflon series materials and the COP polymer materials. These are materials that have been used in industry for a while as internal references generally, and they've been known through experimentation and the literature to basically have very little or no moisture absorption effects. We know that moisture absorption in realistic samples is a problem in terms of reproducibility, so we wanted to do this test with a very stable set of materials so we could really understand what the variability was looking across different labs, so that we could demonstrate the best case scenario in terms of extraction of material parameters to understand how well industry as a whole can do this. So these materials were known, again, to have very little loss, very low moisture absorption. The expectation is that they have very low frequency dependence, and that was nice because, you know, we have methods that span everywhere from 10 gigahertz to over 100, and we didn't want to have a lot of frequency dependence that would confuse the data sets. These are available in optically clear sheets, and that's important because it gives you some guarantee is not the right word, but some confidence that the material surface properties are good. They're also available in appropriate thicknesses. That turns out to be a problem for some materials because these methods have some limitations in the range of thicknesses. And so these two are available in sheet thicknesses that are applicable to these different methods. And they generally have good thickness uniformity. Not perfect, but very good relative to typical packaged substrate material samples that you can acquire. They're also isotropic and homogeneous. That was important because we wanted to eliminate those issues from this experiment, because again, we're looking at sort of the best case scenario here. And so the results from this experiment that we're going to talk about really do represent the best that industry can hope to do with today's current technology and our lack of traceable standards. So if you go on to the next slide. The experiment concluded with measurement of over 2,200 data points in the data set, spanning 10 different labs using these 4 methods and covering frequency ranges from 10 gigahertz to 110 gigahertz. This turned out to be a lot of data to collect. There are 2 materials that we focused on out of this experiment. Again, the COP and Teflon. We provided a very detailed and specific procedure as part of this kit to allow, as much as possible, the labs to perform essentially the same set of material handling procedures to try and eliminate as much as possible variabilities between the measurements. So these kits were created, and we had 10 kits. They were measured at Intel for a reference thickness and also for dielectric constant loss and loss tangent using the equipment sets that we had available at Intel. They were then routed to the different labs, and each lab measured the samples in their kit according to the techniques that they had available in each of the labs. Those kits were then rerouted to a different set of labs, and by doing this, we tried to get as much coverage as possible for each individual sample in the kit, spanning the different methodologies available to us in the different labs. And so there isn't perfect overlap, but there was a lot of overlap for the different samples. And so we have cases where a particular sample was essentially measured by 3 labs using a variety of different techniques. And all of these samples came from the same fabrication batch. So nominally they're the same, but we also had the ability to look at individual samples. The goal of this at a high level was really to understand how much agreement there is in the results from the different labs. Also to understand how well each lab can assess the thickness of these samples. We wanted to understand whether the sample quality was an issue and what the practical issues were associated with handling these types of materials in terms of both providing sizes that were compatible with the different equipment sets, but also just the mechanics of having different lab users handle the samples and take measurements. Because there are a lot of practical challenges that come with these measurements, especially if you're doing a large quantity of measurements, and we really wanted to understand how these materials fit into that picture. We hoped to see if there are any obvious biases between the equipment sets, although that was probably somewhat limited in the sense that we probably don't quite have enough data to look for very small biases between the equipment sets. And then we also wanted to have some idea as to whether our assumption of frequency independence of these materials was really true at the higher frequencies. And all of that sort of points to the question of, do we need traceable standards in industry to drive these types of measurements forward in the future? Okay, so if you go on to the next slide. This is kind of an overview of the results, and if you look back at the reports from this task, there's a lot of additional data and charts that have been broken out, and so there's a lot of detail. I'm just going to kind of cover the high-level results. So this is essentially an overlap of all of the COP measurements that were done, and from this chart, we break it out by the lab and by the equipment set that was used in the individual lab. And I think the key takeaway from this is that, again, given a almost perfect sample of COP material, you can't really expect to get a result that is better than, say, plus or minus 2% in terms of dielectric constant. And the spread and loss tangent you can see from the plot below. This really is as good as we can do as an industry. So if you send your sample off to a lab to have the measurements and you get back a result, this is kind of the error that for sure you at least have in your characterization. We don't have an ability to agree on a value between different labs that's better than, say, plus or minus 2%. If you go on to the next slide, we have similar results for the Teflon. In this case, I think it's a little bit worse, maybe plus or minus 3 or 4%, mostly because I think the Teflon thickness had more variation than the COP materials. But again, the message is the same, that if you want a precision result in terms of dielectric constant, we just really can't do much better than this today, because we have no reference standard with which to all agree upon a true value. Okay, next slide. So is this good? Well, the results are probably better than many of us expected. It turns out that getting reproducible results across labs for any metrology can be kind of challenging. Even within a lab, getting results that are highly reproducible can be difficult for challenging metrologies like these. But for many applications, this isn't good enough. A 2% plus or minus 2% error could cause a design cycle, or it could mean that your customer and the supplier could differ by as much as 4%. And again, this is really for the best case samples. More typical samples are going to have more variability due to issues like thickness variation. Further, if your mean value of characterization of your material samples has an offset due to these metrological issues, that can impact high volume distributions and can push a lot of your, push more material into the fail region of your defect per million outgoing quality controls. So, within Intel, we would notice this kind of a miscorrelation with our design, and we would try and recenter it if we had this kind of an error. So, there are reasons why we, as an industry, should be able to do better than this kind of a tolerance. And again, we're looking at perfect samples. So imperfect samples that are realistic material samples for substrate materials are going to provide more variability. And I also want to note that reproducibility that we've been talking about here really doesn't ensure accuracy. And this is an important thing, because if we had certified standard references, we would have an accuracy assessment. In other words, we could assess how accurate our final result is, as opposed to just what the reproducibility is. And those are two different things. They're both important, but in this case, having accuracy allows us to better align our measurements to our simulation techniques. So it's important that we have both accurate metrologies that are in some way traceable, and also have reproducibility in our metrologies. So essentially, after a year of effort to do this kind of a study, if you look back, if we had a standard reference material available from a national lab, all of these labs independently would have been able to take those measurements on those standards, assess their own reproducibility and their accuracy, and we would have been able to do this very quickly, and we would know exactly the performance of each of these equipment sets independently of having to do this type of an experiment. Okay, if you go to the next slide. So looking back at our goals, how did we do? Well, at a high level, the question was, how much agreement is there in the results? I said for these best case samples, you really shouldn't expect better than plus or minus 2%. And realistically, it's probably worse than that for realistic samples. So if you send your material samples off to a lab, a service lab, to have them characterized, and the lab returns a statement that their results are more accurate than, say, plus or minus 2%, you really need to understand that means that their own lab can probably have reproducibility better than 2%. It has nothing to say about accuracy or about the ability of another lab that also makes that claim to achieve the same result. So, realistically, you can't expect better than a couple of percent today. Thickness. How closely did the labs assess thickness? It turns out that the labs were all using very similar micrometers for assessing the thickness, and we had in our procedure a description of a method where you basically average the thickness measurements of 4 locations on the sample, and we specified specifically where those locations were. And because of that, we yielded a very tight tolerance on our average thickness. So we ended up with something on the order of 0.2 to 0.5% differences in the final numerical results in the thicknesses for each of these samples. And so that's really pretty good. However, it is slightly biased because we did very specifically describe where to take these thickness measurements. And this thickness does end up impacting the final results. With respect to sample quality handling and size compatibility, sample quality, total thickness variation, and flatness is a key limiter to all of these metrologies. It's a key limiter in terms of being able to get samples from material vendors. And the compatibility of sample sizes and thicknesses between equipment sets is very challenging. It turns out to be a very challenging practical problem to get samples that have all of these qualities and are compatible with all of the different equipment sets. And that's, again, points to why a reference standard would be so helpful. In terms of understanding the practicality of these techniques, it's very clear through this experiment that if you're a lab that is starting out or have limited experience and maybe not a lot of practical skills, or if you're working on a large quantity of measurements, the SCR and SPDR techniques are very much less operator sensitive and are relatively easy to use and fast. The benefits that you get from the more advanced techniques like FPR and BCDR in terms of their ability to characterize out of plane and anisotropic behavior, they require more expertise and experience. There are definitely benefits there, and there's a lot of really interesting capabilities, but they're not probably the instrument that you want to start out with if you're beginning to do this. In our efforts to look for obvious biases between the equipment types, we didn't see anything that stood out given the limited sample size that we have. I think for the biases that we would be looking for in these equipment sets, we would probably need to have a reference standard that was flatter, and also we probably have to have more measurements. The only case where this became obvious was in the industrial materials, and that will be talked about in task 4, where the anisotropy is clearly visible. In looking for frequency dependence, we didn't see any sharp COP or Teflon frequency dependence, which I think was expected. However, without the traceability, we don't have a lot of confidence in this statement as to what level, how flat this is exactly. And we had to rely heavily on BCDR and FPOR for the statements. And it's possible that there, could be some frequency dependence is just not obvious in the data because of the spread that we have inherently in the different measurements. But in any case, there isn't a lot of frequency dependence if there is any. So do we need traceable standards? I think throughout this whole experiment, it became more clear that having traceable known reference standards would enable a lot of these measurements to improve and would further industry's ability to develop new advanced techniques that are, perhaps the next generation. So we do need further work in this, and that will really allow us to have higher confidence results in future techniques. Okay, if you go on to the next slide. I mentioned that sample quality is an issue, and it continues to be a measurement challenge. These samples are very thin because of the frequencies involved, and so only a few microns of thickness variation can end up contributing percentages of results to the final answer that you get. And commonly available material thicknesses have variations that are on the order of many microns. It turns out to be very difficult to get super flat uniform samples. And so this is something we need to keep in mind as we move forward, that the sample quality and the issues associated with thickness are probably a leading area for improvement. If you go to the next slide. There's a few additional complications when we looked at the realistic samples that'll be talked about in task 4. Most of the labs use high precision micrometers. These tend to have a relatively limited throat depth. So for example, if you look on the picture on the right, most of the time you have to measure the samples somewhere near the edge. And in a lot of the measurement techniques, the fields that are used for extracting the dielectric constant are in a region that you can't physically measure with a common micrometer. Drop gauges can improve upon this, but they also have limitations. So this idea of assessing the thickness turns out to be an important place where we might be able to, in the future, make some improvements. We also found that some of the techniques are sensitive to bows in the material samples. And so it's not always easy to make the realistic samples perfectly flat when you put them into the equipment sets. So moving forward, we probably need some advancements to try and address some of these problems that I've categorized as less interesting in terms of technicalities, but they're very practical and they lead to significant errors in the assessments. And they generally affect all of the measurement techniques because all of them rely on understanding the material thickness and in most cases assume some flatness. Okay, if you go on to the next slide. So is COP or Teflon a good candidate for a standard reference material? Probably not. The challenges in getting sub-micron thickness variations of these samples is very high. They're soft and relatively easy to scratch, and that has potential challenges with traceable dimensions. COP is known to degrade with oil contact, so that leads to difficulties ensuring stability over time. And neither of these can be metallized for use with transmission line structures that are important for other applications. They are commonly used today as non-traceable references, and they're good options until a traceable standard is available. And in the future, we see that these materials will be really helpful for transfer standards after a standard reference material is available, because you'll be able to take a calibrated instrument that's calibrated using the standard reference material and then measure an individual sample of these materials and sort of use them as transfer standards. And because they're easily cut to size, it makes them easily usable in other test devices, and that will enable development of new devices that have some connection to a traceable standard. They're also easy to handle and generally not breakable, so they're good for routine lab use and quality checks. Go on to the next slide. So sort of the summary of task 3, don't expect anything better than plus or minus 2% in dielectric constant measurements, and that really is a reproducibility number in the best case situation. There's a number of contributions to this, and none of them are totally dominant, and so we need to make improvements in several areas to squeeze the performance out of this. We did find that barring information that you may have about a particular lab, using samples that are 35 by 45 or 90 by 90 tends to fit most of the equipment sets. And the thickness varies by this dielectric constant and the specific device that you're going to do the measurements with, but typically 100 to 250 microns is commonly useful for many of the organic dielectrics. So if you don't know what exactly or where you're going to get your measurements done and you're asked for a dielectric sample, your best bet is to request something in the 100 to 250 micron thick range and in the 35 by 45 or 90 by 90 form factor. And then you'll have a reasonable number of options at which to get measurements made. But the overall summary is that we really need traceable standards and improved thickness measurement techniques in order to drive these technologies forward and to make improvements in dielectric constant measurements. And with that, we'll move on to task 4, which is an overview of the realistic material sample measurements.
Yes, thank you, Mike. And we're going to move on, I think, to Nate or Lucas. Just wanted to let you know that we are going to continue on a little bit beyond the hour, because you can see we have a lot of data and important topics to discuss. The meeting was scheduled for 1.5 hours. We'll finish the presentation at the top of the hour and leave some time for question and answer. So we have 15 minutes allocated for the commercial measurements. So Nate?
It's actually me.
Okay. Hi, Lucas.
Hello. Sorry. Yeah, I'm Lucas Lenright from NIST. Sorry, I will go very quickly to try to be respectful of your collective time. But some quick overview and objectives of task 4. Mike just talked in great detail about task 3, where really we were looking at evaluating COP and Teflon as sort of quote unquote golden units. They're very well behaved, very low loss polymers that many people are currently using as sort of interim references in lieu of traceable standards. In task 4, we wanted to take our findings from task 3 and really validate them and ensure that they apply to real materials, which we had submitted by industry representatives in this group. So additionally, in task 4, we included fused silica and Rexolite, both of which are sort of interesting materials to look at for potential standards. And really, just our goal is to validate the findings of task 3 and show that the same exact findings come out of measurements of real materials from a couple sectors of industry. If you could go on to the next slide, Ermi. Thank you. So the first sector of industry we really looked at was the electronics industry, which is really highly represented in this meeting. And so our samples from the electronics industry, we had 34 of them, and they came from 7 different companies. And they had a broad range of thicknesses and dielectric constants within what's reasonable for sort of typical substrate materials. So we had thicknesses ranging from, about 60 microns to 300 microns, and dielectric constants from about 2 to 5. And these materials also added some anisotropic samples, which we did not see represented in the task 3 samples. Additionally, you can see on the left just sort of a photo of the sample kit. And we had all of our samples broken into either 35 by 45 millimeter coupons for some of the smaller measurement setups, and 90 by 90s for the Fabry-Perot and BCDR instruments. Additionally, we had the automotive sample kit, which added a lot of kind of challenges that we couldn't extract from the electronics materials. And so shown here on the right is just photos sort of the two clusters of automotive samples we had submitted. So on the top are these sort of bumper materials that were up to about 4 millimeters thick, which is obviously way thicker than our typical electronics materials, and added some measurement challenges. And on the bottom, we had some of these foils, which were substrates, some of which had thin films on top of them. So those were between 100 microns and about 600 microns all told. And so both of those things, the thicknesses and these sort of thin film composites, both really limited our measurement options because they add a lot of complications that well-behaved traditional substrates don't. If you go to the next slide. Thank you. So for task 4, we scaled down the number of test labs, mostly for efficiency and schedule. So there were 3 labs from the US in Keysight, Intel, and NIST. And in Europe, we had labs from Qued and Nokia. And while the labs making the measurements were only represented in the US and Europe, we had samples submitted globally from the US, Europe, and Asia. So our key takeaways really sort of mirror those of task 3, thankfully. So the sort of the key two, in my opinion, are that with just 2 different sample sizes, the 35 by 45 millimeter samples and the 90 by 90 squares, we're able to sufficiently measure all of these materials with all 4 of our techniques of interest, the SPDR, SCR, BCDR, and FPOR. Additionally, we, like Mike just highlighted, we really found that the thickness evaluation and thickness variation within a sample were both huge indicators of the kind of variation we could expect out of measurements on a given sample. And sort of with that in mind, we were seeing results variations in real samples on the order of 2 to plus or minus 2% to plus or minus 5%. Most of those, unless it was something that was anisotropic, are right around plus or minus 2%. Some of them even did better than that. But particularly when you start including anisotropy, some of them had potentially unexpected anisotropy. We did get into those higher numbers, and a lot of those also were materials that had some interesting variations in the thickness measurements themselves. Additionally, in this task, we were really interested in looking at these candidate standard reference materials. I particularly was interested in looking at the results from FuSilica because that is sort of the leading candidate for the standards development. So with that, a few really quick disclaimers. Compared to task 3, we have fewer labs, and so there were a total of 5 labs involved in this study. And because of the instrumentation limitations, there was a maximum of three labs on any one physical sample. So to overcome that, we compared samples that were cut from the same sort of sheet of material that was submitted to us. So we might compare a 35 by 45 to a 90 by 90 if they were cut from the same sheet of material B submitted by any given company. Additionally, there's a very large overlap in the instrumentation being used by each of these labs. You can imagine there are only a few vendors that have these resonators commercially available. So there wound up being significant overlap in labs using SCRs and significant overlap in labs using FPORs. Additionally, something that's different from task 3, we are all using the same measurement kit. So sample to sample variation isn't quite as well captured. That it makes it so that we can more directly compare the microwave side of our measurements. But if you were to blindly submit a sample of your material to 3 different labs, that variation would not be captured in this study quite as well. Lastly, there's sort of an asterisk next to this one, but we're all using the same thickness measurements. Each lab did more or less make their own thickness measurements as well, but for the point of comparing all the microwave side of the measurements, we use the same thickness measurements from Intel so that we could really focus on the microwave side of things. This really removes the variation coming from the different thickness measurement capabilities of each lab, because that's something that we had already acknowledged was problematic. But like I mentioned before, we did also make those measurements at some of these labs. And so I do point that out in a later plot. If you go to the next slide. Thank you. All right. So here, this is a very overwhelming plot. I apologize, but really we're just showing all of the data points at once from task 4. So you can imagine there's quite a few of these. I think this is just the electronic samples, and there's a few over 1,000 points on here. Highlighted on the left, there's that task 3 range in the real part of permittivity, showing that for the COP and PTFE measurements we made in task 3, we really only covered real parts of permittivity between 2 and 2.5. And in task 4 here, we show that obviously we're going from overlapping with that range slightly all the way up to a permittivity north of 5. Additionally, we have on the right, you can see a huge range of loss tangents shown all the way down from 1e minus 4 to about 1%, which is really a tremendous spread. So just in the electronic samples, we're covering a huge range of frequencies and a huge range of material properties. If you go to the next slide. All right, so the first one that I have a personal interest in for obvious reasons is the fused silica, which is the prototype standard. Or if you could click through this one fairly quickly, actually. Really, the thing I'm trying to highlight is that we had an overall spread of about plus or minus 0.4% if we're all using the same thickness, which is really, really narrow and really great for showing that we have high reproducibility. But the disclaimer to that is, again, we're all using the same thickness measurements, and most of these are made with SCRs from the same vendor. If you go to the next one. One more. Sorry, this is a little inconvenience to make you steer. Right, so really what I'm trying to highlight here is just that if we add in additional thickness measurements from one of the labs, with just about a 1.5% difference in the measured thickness, it's not even 2 microns difference in the measured thickness, we're getting about a 1.5% difference in the measured permittivity just from that. So really, these thickness measurements do have a tremendous impact on our extracted microwave properties, even though they're not the most exciting problem to address. If you go to the next slide. So with that, I kind of bounded these. We can click through these pretty quickly, but I bounded these by the lowest thickness, the highest thickness, the lowest permittivity, and the highest permittivity of the real materials we measured. So here we have the lowest thickness we measured at about 60 microns. You can see at the top, those points in the real part of permittivity are all very tightly spread. And then something that I think is sort of exciting is that if we add in the BCDR measurements, which is measuring the out of plane permittivity, it's uniquely doing that compared to the other 3 measurements we considered. You can see this out of plane permittivity that's more or less 10% lower than our in plane measurements. But otherwise, they're all grouped very nicely. And additionally, our loss tangents are all grouped pretty nicely. So we've shown that we can measure really thin stuff pretty well. Sorry, that was really fast. The upper boundary for thickness at about 300 microns is also very conveniently our lowest permittivity. So I saved the chaos of one more slide. But this material, we saw pretty consistent results for any given physical sample. The biggest determinant in this one seemed to be thickness variation within samples and from sample to sample. And this material is something that is very known for being difficult to thin. It was something we kind of expected to have some thickness issues going into it. So to be honest with you, the fact that we wound up with a plus or minus 4% spread, I thought was pretty reassuring. So the upper boundary for the permittivity, because we just covered the lower boundary for the permittivity at the same time as the highest thickness. The highest permittivity material had a permittivity of about 3.8. It's very reproducible in that range. We had no problems with the high permittivity. And again, actually, you can see sort of there's this large cluster of outliers at the bottom. And that is just presumably from the anisotropy being captured by the BCDR measurements. So it's really interesting to see that those fall out and land so nicely grouped at just about 10% lower. We can sort of skip through this. Essentially, I was just impressed that we could measure the thickness test glass, which was just some sort of less well-behaved microwave material glass. And we were able to, even while really pushing the limits of these resonators in terms of permittivity, thickness, and loss all at the same time, we were still able to get pretty good results up to about 40 gigahertz. And this just sort of shows what happens if you really absolutely break your specifications on your resonators. So here are some materials we expected to be anisotropic out of plane. The previous ones I showed were not expected to show that, but happened to. And so these ones, again, we can just capture and show that there is a slight out of plane anisotropy. The anisotropic, or excuse me, the out of plane permittivity is, again, lower than the in plane. And it's just interesting to see these BCDR points. And it's very important to note that that is effectively a different measurement of a different material property, really, even though it's the same material property, just in a different direction than all of the in-plane measurements. Additionally, we were able to show that some of these materials had an in-plane anisotropy, so just sort of rotating X and Y within the plane of the sample. We were able to capture that with the Fabry-Perot setups because that uses a polarized field. And so you can see on sort of the right-hand half of, well, really the entire real part of permittivity plot here, you can see that Intel and Qued's Fabry-Perot measurements, those circular dots, all capture two different directions of the sample, two different orientations, and therefore show that we're capturing the in-plane anisotropy very repeatably. And then I can't really speak excellently to these automotive samples, but just showing that we can make these measurements, Qued was able to, with those ridiculously thick, 4mm thick plaques for the bumper materials, Qued was able to make measurements with their SPDR and FPOR with good repeatability. And those are on the order of real part of permittivity of 2.8. Ermi, if you want to go to the next slide. The other really challenging samples included in the automotive kit were these sort of thin film composites. So on the left-hand side, we're showing the real part of permittivity, the dielectric constant, and the loss tangent of those, the blank substrate, and showing that those are grouping pretty nicely. The BCDR points kind of zero down into a consistent value, and the loss tangent seems to more or less agree. And then on the right-hand side, we're showing that same substrate with a thin film coating on top, and showing that different effective in-plane parameters are extracted from the SPDR and FPOR, and then out-of-plane parameters are extracted from the BCDR. So really just showing that we can make these measurements on much more challenging materials. Sorry, you're good. All right, so really, again, just highlighting our key takeaways, we're able to measure the real materials just like we can measure the PTF. I muted myself at some point in that sentence. Sorry, but the result variation is more or less what we saw again from the candidate standard materials. It's maybe a little bit higher spread, and a lot of that is coming from these thickness challenges, whether it's the measurements in the thickness or thickness variation in the samples themselves. Thankfully, we didn't have any really unexpected challenges in terms of any of these materials having a shelf life or any of them being extremely difficult to handle. And we were able to measure a broad range of thicknesses and permittivities, going from about 60 to 300 microns in thickness, and real part of permittivity of about 2 to actually about 5. And we were able to do that with just the 2 sample geometries, so it's really easy to prepare these. And additionally, we've shown that we can measure way more challenging materials if we have adequate time to develop these specific setups. Next slide. Awesome. Okay, so Ermi, this is really your slide, but I can go through it if you'd like. So really the big limitation we found is that currently there are no niche traceable standards. Previously, there was a standard for the permittivity and loss tangent in SRM 2870, but that was discontinued in recent years. Instead, we do currently offer standards for peanut butter and dry cat food. I believe there's also one for spoiled food. Not to take away from the value of any of those things, but it does seem silly that we don't currently offer something for these fundamental material properties in Rexolite. So kind of as an overarching question, why don't we just relaunch that same SRM? And if you go to the next slide, we can discuss that in a little bit better detail. So really the largest issue that I see with them is that that previous material that we used in order to be reasonably thinned down to a sort of a reasonable thickness variation within a given sample. I'm sorry, if I can restart that sentence. It was very difficult to have them thin enough while maintaining a thickness variation to be practical for these measurements, for these resonator measurements that are relevant to these low loss millimeter wave materials. And additionally, they're really only certified up to 10 gigahertz, which is way too low for the frequencies of interest for this group, being at millimeter wave and being in that kind of 20 to 80 gigahertz range. And so today, all permittivity tool vendors are they're currently running without any kind of traceable standard for validating their tool sets. They're using these sort of interim standards, typically the COP and the Teflon, as well as some of them are using sort of machined Rexolite, which is this former standard, and Fusilica. So with that, kind of where do we go from here? I'm going to shamelessly shill for the next iNEMI project, which I have a very personal interest in, which is the development of a reference material, a traceable reference material for these millimeter wave frequencies with a particular focus on the 5G bands. There's a project kickoff on June 16th, which I believe will be a very similar meeting to this. And with that, you can certainly kick Ermi, excuse me, you can certainly contact Ermi for further info. Please don't kick Ermi. For further info on involvement with that. So thank you all for your time. Ermi, I think I can turn back over to you.
Yes, thank you so much, all the speakers. I know we went a little bit beyond the scheduled time for the scheduled presentation, but I think you can, hopefully see the amount of work in this project, as well as what I personally am very thrilled about is this, multiple different groups participating in validating a lot of measurements. I actually am also very, very happy to say that we have so many, so to speak, practical commercial materials also measured and demonstrated the validity of techniques, because in general, this wasn't a research project. This is an industry sponsored project